Yes. Oh, oh,
Go ahead,
uh,
Kartik. Yeah.
no, I missed my slide. Something. Yeah, I cannot see my slide.
Maybe try to stop sharing and sharing again. That might work sometime.
Yes. Yes. This is a joint work with my thesis advisor Vivek Mohan Malli, and due to some emergency, he could not make it. So I thank the organizing committee for being so understanding and letting me replace Vivek. So the plan of the talk is we talk about toric varieties a little bit, and then we define T varieties and define multi-homogeneous space and present our work and conclude. So start with normal variety over complex number of dimension D and an algebraic torus of dimension K. We assume that the torus acts effectively on X. So this corresponds to there being being a point in X such that the orbit of that point is isomorphic to the torus as a variety. We have special cases here like when K is N, the effective action of the torus on the normal variety X ensures that X is a toric variety, which can be described in terms of combinatorial data. Uh, yes, which can be described in combinatorial data. And if you have an action of a torus on an affine variety that correspond to grading of the ring of global section by the character lattice of the torus. And yes, so out of all geometric objects, the projective varieties are nicer in terms that there exists an affine cover induced by homogeneous sections. And to mimic this ordinary construction of projective varieties, David Cox defined a ring corresponding to a toric variety, a special toric variety. So here we start with the n-dimensional toric variety, and there are toric varieties which are not normal, but throughout this talk we assume all the toric varieties are normal, and that leads to the Chow group n-1 x being Picard isomorphic to the Picard group, and we further assume that it is free. And let sigma 1 be the set of rays, and each ray defines a torus invariant prime well divisor d rho. So and one more thing is that this Picard group is generated by these d rows, and it says the number of rows has to be greater than the rank of the Picard group. And I said that David Cox wanted to mimic the ordinary projective construction of polynomial or n-graded rings. So here he defined a ring corresponding to each ray. He chose a variable, and we have this ring in d many variables, or row i's are rays, and trivially one can define the degree of this polynomial ring. So you start with the monomial and replace the variable with corresponding well divisor d rho, and take the translation given by the power and take the direct sum. It becomes an element in the Picard group. And as I told you that the Picard group is generated by this d rho. And we have this short exact sequence, and M being the kernel, and taking the spectrum of this short exact sequence, we get a short exact sequence of torus. we assumed the Picard group to be free, so G is torus. And G sits inside this bigger torus, C star sigma 1. And C star sigma 1 acts on spec of S trivially because of this grading, defining the degree of xi to be 0. So
wait, Karthik, what this D is? What number of vertices in the fan? What is the D exactly?
small d.
Yeah, small d.
And d is the number of rays in that fan, sigma. Sigma is the corresponding fan uh, associated to the toric variety X.
Okay.
Yes. Now, I told you that C star sigma 1, this bigger torus acts on spec of S, and G sits inside this bigger torus. So G acts on a spec of S. Okay. And once you have an action and G is torus, so it's reductive group, you can talk about you can talk about quotients of this action. And David Cox defined one such quotient. He did on the ring side, he took this ideal generated by X row, product of X rows are outside particulars sigma, and sigma varies over all the fans in sigma varies over all the cones
Hi,
in.
Kartik, I just have a quick question. So, what do you mean by C raised to sigma of 1? Is that C raised to D, or what
Yes,
is the notation?
yes. So C star raised to sigma of 1, it should be like it has a typo, so it should be D. Yes, the
Okay,
number
okay.
of rays.
Right. Okay. Thanks.
Yes. And so we have this ideal, and one can see that this ideal is invariant under the action of G. And and if you take the vanishing of this the locus of this ideal, that becomes invariant under the action of G. So the complement is also invariant under the action of G. And we have this thing that X is isomorphic to the categorical quotient of the uh, of this open locus of C to the power sigma 1. So this means that C to the power T, and removing the locus Z. And one more thing is that this quotient, categorical quotient, is isomorphic to X, and this categorical quotient is geometric if and only if X is simplicial. So it is work by David Cox. And one more thing is that once you have this correspondence that simplicial toric varieties are coming from a ring mimicking the Prost construction for ordinary projective spaces, you can talk about whether the coherent shifts or quasi-coherent shifts on this toric variety are coming from the modules or modules over that ring S. And that happens also. So here we have this thing that graded S module correspond to quasi-coherent OX module. And this functor is exact and essential surjective when X is simplicial. So we have this nice analogous result for toric varieties, simplicial toric varieties. And next, moving to the next part, we define T varieties. So toric in toric varieties, that a torus acts on that variety, and the dimension of the torus is same as dimension of the variety. So generalizing this idea, we have this T variety. T varieties, and these are like varieties with a torus with an effective torus action, and the dimension of the variety and the dimension of the torus may not be same. So, and the action being effective means that dimension of the torus has to be less than equal to dimension of the variety. and we call the difference the complexity of the T variety. And as you can see that zero complexity T varieties are tori varieties.
Is that the definition of effective action? Is the dimension of torus is less than equal to the dimension of variety?
No, it's just a corollary of that action. Yeah, one can prove that if you have the dimension. So if I told you that effective action means that there is a point, or you can say there is an orbit in AX such that T is isomorphic to that orbit as a variety. Okay. And the dimension of that orbit is dimension of T. And if you have dimension of the torus is bigger than dimension of the variety, then you have you cannot have a closed subvariety inside a variety of bigger dimension, right? Is it okay?
Yeah. Go on.
Yes. Okay. And so complexity 0 T varieties are toric varieties. And so one can ask whether T varieties can be described combinatorially like the toric varieties. And here we have a description given by Altman, Hausen, and Seuss. They define that every T variety can be described combinatorially with two things. Like one is you must have a semi-projective variety Y, and you have a fan of polyhedral divisor on Y. I'll say what is a polyhedral divisor, and we can explicitly say the dimension of the semi-projective variety Y given the dimension of the torus and the variety dimension of the variety X, and the dimension is exactly n minus k. And so we know what are ordinary divisors, right? So it's like you have prime divisors and you take linear combination of prime divisors with integer or rational coefficients. So you just replace those integer or rational coefficients by polyhedra. And a polyhedra is nothing but intersection of finitely many closed half spaces. And one equivalent definition is that polyhedra is you have a cone in the lattice, and you have a polytope, which is the convex hull of finitely many points, and you take the Minkowski sum of this cone and that polytope, you will get a polyhedra. And here we have a polyhedral divisor, means we have a prime divisors, and you take the linear combination of prime divisors with coefficient in polyhedral divisors. So the coefficients are not integer or rational numbers, these are polyhedra, but their tail cone are same, it is sigma. And this description corresponds to affine T varieties. So if you have affine T variety X, then you have a Y and a polyhedral divisor, fan of polyhedral divisor. And like ordinary fans or cones, you can also have the faces of polyhedral divisors, and these faces of polyhedral divisors correspond to open embeddings of corresponding varieties. And this whole construction generalize the ordinary construction, combinatorial construction of toric varieties. And here we define the generalization of Prost construction. And ordinary Prost construction is graded by natural numbers, and we define here the Prost construction for higher graded rings. So we assume D is a finitely generated abelian group and S is degraded ring. And out of S, we get some rings, which, so now this grading correspond to the action of spec of D on spec of S, and we can ask whether that action has geometric quotient. But in general, it does not happen that you have a geometric quotient, but there exists some geometric quotient if you have if you choose some suitable locus, and those locus are given by the localization of the ring by certain homogeneous elements. So we call S is periodic if the degrees of homogeneous units form a subgroup of finite index. So if you have a periodic ring, then you know that S is a principal homogeneous bundle over S naught, and you have the geometric quotient given by spec S to spec of S naught. And here, since most of the rings don't have these properties, that all the homogeneous elements, homogeneous units, they induce a subgroup of finite index, we go to some localization of that ring that have those properties. So we say an element is relevant if it is homogeneous and SF is periodic. Now SF being periodic implies that spec of SF uh, admits a geometric quotient. And here we define DF. DF is basically you have all the homogeneous divisors of F, and you take that their degree and define the cone induced by them. And here is the S round bracket S. F is the geometric quotient, not is the degree 0 part of SF, and because it's being a principal homogeneous bundle over S round bracket F, this is a geometric quotient of a spec of SF to spec of S round bracket F, and this action, the global action spec of D on spec of S, does not have a geometric quotient in general. I mean, and yeah, the quotient space does not lie in the category of scheme, but it lies inside the category of ring space, and this is the quotient code S. This is the quotient of this action in the category of ring spaces, and we have this scheme inside that category, inside that quotient. And we define proj of the ring to be this union of these locally geometric quotients inside that quotient of category in categorical quotient of ring spaces. And this is by definition, by definition is a scheme. And here we have a theorem that if you have a degraded ring and proj is non-empty, then one can define the modules as usual OD. And further, we have this property that OD are coherent and reflexive shifts, and we know they are global section. Those are isomorphic to AD. And furthermore, that if D, the shifting is such that it belongs to the cone of every relevant element, then OD is a line bundle. So for ordinary projective spaces, we know that all the shifting are line bundles. For weighted projective spaces, we know that all the shifting are not line bundles. Only the scaling of the LCM of the degrees, if you take the LCM and that multiple, those are only line bundles. But every shifted module is a reflexive shift, and their global sections are AD. And obviously this recovers and this generalizes similar results on weighted projective spaces. And here we define the relationship between T-varieties and MHS. So M is a lattice and A is a M-graded ring with pointed weight cone. Weight cone is basically, so you have a grading and you take all the degrees where A that corresponding homogeneous part is non-zero. And we assume that A naught is C and A is finitely generated over A naught. And spec A is a T variety with effective C star D, this torus action. So, yes, because of this is a T variety, we can describe it with equivalent definition by this pair Y comma D. Y is a semi-projective variety and D is a fan of polyhedral divisor. And we have this result that there is a birational morphism from Y to proj of A, and A is the M-graded ring. Furthermore, D can be described in terms of the shifted modules on proj A. And so there is one thing that I told you that David Cox he started with a simplicial toric variety and got a ring, and from that ring he constructed that toric variety as a geometric geometric quotient. So Parling also generalized this Cox construction, and he extended that result to bigger class of toric varieties, and his construction is known as T-pros. And if you have a toric variety, and if you take the ring Cox defined by Cox, then that is graded by the Picard group of the toric variety, and from there you get three things. One is by T-pros construction you get that original toric variety, and because that is graded by Picard group, so spec of Picard group has action on the spec of ring, and you can think of that as a T variety, and you get this Y. And because also because that is graded, you have this proj of A. So you have three things, and the result is that all the three things are birational. And one more thing is that if you have this lattice and A is integral C algebra, and the X is the corresponding variety, omega is the weight cone, then for a point we define the cone. That is basically you have a homogeneous section that is locally unit at X. So if you have a homogeneous section F with degree U, and F is locally unit at X, we take that degree and generate we generate a cone by those degrees. This is called the weight cone of the point X, and these weight cones fit in a nice setting. Like these weight cones gives us GIT cones, which are defined like this. So you have a point, and if you have a homogeneous section at U, you take the weight cone of X, and this overall intersection gives you the GIT cones, and these cones uh, fit in a fan. So this cone, all the cones are in, they constitute a fan. And we have shown that if omega is a GIT cone, then Y is projective, and the birational map between Y and proj is an isomorphism. So if you have omega is a GIT cone, then this is a unique full dimensional GIT cone, and that says that then the T variety Y has to be projective, and the birational map is an isomorphism. And yes, and the examples are product of weighted projective spaces. Thank you. And here are some references.
Okay, so let's thank Kartik Roy for his talk. And if there are questions and comments, please raise your questions and comments. So if there are no questions, let me ask some questions.
Yes.
So I missed your lecture by a few minutes in the beginning. So but I saw somewhere that your field was complex number. Is that correct?
Yes, so we assume that S naught is complex number. Yes, yeah.
So
Okay.
why do you have to assume this? Because everywhere you deal with fans and cones, which are some combinatorial gadgets. So what has it got to do with the field complex numbers? Why not over other fields?
Okay. So some of the results pass smoothly to other fields, but we are just considering varieties over spec of C. So that's why I took complex numbers.
Yes. So are you saying that whatever results you had, they will also makes sense over, I guess, over arbitrary fields.
I also think, but maybe not all the results, only some of the results pass to arbitrary fields. We actually are interested over varieties over complex numbers, so that's why we fixed that field to be complex numbers.
And one more question I had was, maybe you defined it somewhere, but I couldn't see it. So there was some term called semi-projective variety. So what does that mean?
Semi-projective varieties?
Yes.
It's yeah, open subvariety of a projective variety.
So you take any open subvariety of a projective variety.
Yes.
That's called semi-projective variety. I see. Okay.
Yes.
Oh, okay. I see. So fine. So yeah. So yeah, I believe that whatever you said, I don't see any obstruction in doing this over any field, in fact, over any ring. So maybe
Yes.
you may like to consider that.
Yeah. Okay. Okay.
Okay.
Yes. Thank you.
So yeah. Okay. So I had another question. So somewhere you said you had some group G, right?
Yes. Yes.
What was that G?
G.
When you said that something is some ideally invariant and there's G, what was that G?
G was so you have this Picard group. This Picard group. Okay.
Yes. So is this G a discrete group or what?
No, it's a torus because I assume the Picard group to be free.
So how does a torus act on an ideal?
No. So
because I remember you said that some ideally invariant under the action of G, so I got lost. So what do you mean by
Okay, so here is the thing that so here we have this ring S. Okay, and here we have this Picard group. So I told you that action of algebraic group action correspond to since our group is affine, this action correspond to the grading of the global section of this affine variety to the so this action correspond to the gradation of this Picard group on this ring, and this grading is given by this definition. So once you define that this ring is graded this way, you immediately gets action of G on spec of S. And since this grading actually fitted this into this short exact sequence, so this action is actually factoring through this bigger torus.
Okay, so you mean that action in terms of Hopf algebras?
Sorry?
So I guess you meant the action of G on the ring in terms of you were saying that the coordinate ring of spec of S being some kind of Hopf algebra, right?
Hopf algebra. I don't know Hopf algebra. Also, you mean that in terms of co-multiplication?
Yes, right. Because the multiplication in terms of group action on your affine variety is equivalent to having some Hopf algebra.
Yes.
I guess you meant in that sense.
Yes.
Oh, okay. Thank you. So let's end this session. Let's thank Kartik Roy again, and we will resume in 8 minutes at 14:40.
Okay. Oh, thank you.